Somewhere, right now, floating a million miles from Earth, a telescope the size of a tennis court is staring into the deepest darkness humans have ever managed to look into, and what it keeps finding shouldn't exist. Not shouldn't exist, in some poetic, exaggerated sense. Shouldn't exist according to the actual physics we've relied on for decades to explain how the universe built itself. Astronomers have started calling these objects little red dots, a name that sounds almost cute, almost harmless, until you understand what one of them actually turned out to be, a black hole, not an ordinary one. A black hole so massive, sitting so early in the history of everything, that it's forcing some of the most respected astrophysicists on the planet to admit, on the record, that something in our model of how the universe works may be broken. Before this pulls you any further in, here's the honest foundation it's built on, because space content online is packed with fake urgency, fabricated, just detected headlines, and breathless claims that fall apart the moment you check them. This script isn't going to do that to you. What I'm about to walk you through is real. It's recent, some of it published within the last several months, and it centers on one of the strangest, most genuinely unresolved puzzles in modern astronomy. Black holes that appear to be too big, too soon, sitting at the edge of what our instruments can see and at the edge of what our theories can explain. To understand why this matters, you first need to understand what the James Webb Space Telescope actually is, and why astronomers treat every new image it sends back as a potential earthquake for the field. Webb launched on Christmas Day, 2021, and reached its final position about 1 million miles from Earth, roughly a month later, parked at a gravitationally stable point in space called the second Sun-Earth Lagrange point. Unlike Hubble, which observes primarily invisible light, Webb sees the universe mostly in infrared, and that distinction is the entire key to why it's rewriting textbooks. Light from extremely distant objects gets stretched as the universe expands, shifted from visible wavelengths into infrared, a phenomenon called redshift. The more distant and ancient the object, the more extreme that shift becomes, which means an infrared telescope isn't just seeing a different kind of light. It's seeing further back in time than almost anything that came before it, because the light hitting its mirrors left its source when the universe was young, sometimes staggeringly young, and has been traveling toward us for billions of years just to arrive at exactly this moment. That's not a metaphor. When Webb photographs something 8, 10, 13 billion light years away, it is not showing you what that object looks like today. It's showing you a snapshot of what it looked like the moment that light left it, which means Webb is, quite literally, a time machine pointed backward. And it's within that time machine, looking back toward the very beginning of everything, that astronomers started noticing something that, frankly, wasn't supposed to be there. The trouble started almost immediately after Webb's first science images were released to the public in the summer of 2022. As astronomers began combing through the data, they kept finding galaxy candidates sitting at redshifts, meaning distances and ages, that put them impossibly early in cosmic history, and those galaxies looked far more massive, more developed, and more mature than any existing model predicted they had any right to be. One astrophysicist studying galaxy evolution summed up the growing unease in the field with a sentence that's now become something of a rallying cry among researchers grappling with this problem. Webb is finding too many, too massive galaxies, too early in the universe. 3 twos in a row, stacked together, from a scientist who studies this for a living, not a headline writer trying to generate clicks. That's how strange this data has looked from the very beginning. But galaxies being unexpectedly massive was only the first crack in the wall. The deeper mystery, the one that's dominated cutting-edge astrophysics research through 2025 and into 2026, is what's sitting at the center of some of these ancient, distant objects, supermassive black holes, growing far faster and reaching far greater masses than the standard model of black hole formation says should be physically possible in the amount of time available. Here's why that's such a serious problem, and it's worth walking through the actual physics rather than just asserting that it's shocking. In the traditional model, astronomers have relied on for decades supermassive black holes, the kind that sit at the centers of galaxies, including our own Milky Way, don't start out supermassive. They start as what's called a stellar mass seed, formed when a massive star runs out of fuel and collapses in on itself. That seed black hole then grows slowly over enormous stretches of cosmic time by consuming surrounding gas and merging with other black holes, gradually climbing from a few dozen or a few hundred solar masses up toward the millions or even billions of solar masses we observe in supermassive black holes today. That growth process takes time, a lot of time. Billions of years, under most conventional models, to reach the kind of mass astronomers were finding. The problem is that Webb kept finding black holes with masses in the millions, and in some cases estimated in the tens of millions of solar masses, sitting inside galaxies that existed less than 1 billion years after the Big Bang. In one case that made headlines across the scientific press in 2026, researchers using Webb confirmed an actively growing supermassive black hole inside a galaxy just 570 million years after the Big Bang, in an object now cataloged as Canucks ALRDs A8.6. To put that time frame in perspective, if you compress the entire nearly 14 billion year history of the universe into a single calendar year, that black hole would have already been actively feeding by around January 15th. Barely 2 weeks into the year, and there's already a black hole out there so heavy that its host galaxy, itself the most massive galaxy known to exist at such an early time, still can't seem to grow fast enough to catch up with it. That last detail is the part that genuinely rattled researchers, because it breaks a relationship astronomers have observed and trusted for decades. In the nearby, modern universe, there's a well-documented link between the mass of a galaxy and the mass of the supermassive black hole sitting at its heart. Bigger galaxy, bigger black hole, in a ratio that holds up remarkably consistently across countless observed systems. It's one of the quiet, elegant patterns that made astronomers feel like they understood, at least roughly, how galaxies and their central black holes grow up together, feeding off each other, evolving in tandem. But in Canucks LRDs A8.6, that pattern breaks. The black hole is overmassive compared to what its host galaxy's size would predict, meaning it appears to have grown dramatically faster than the galaxy surrounding it. One of the researchers involved in analyzing the discovery put it plainly. The spectral features revealed by Webb showed clear signs of an accreting black hole at the center of the galaxy, something that simply could not have been observed with any previous generation of technology. The fact that this black hole is overmassive relative to its galaxy suggests black holes in the early universe may have grown much faster than the galaxies hosting them, not slower, not in step, but faster, racing ahead of a process. Astronomers thought was supposed to be a partnership, and Canucks LRD Z8.6 isn't an isolated fluke. It's part of a much larger, deeply strange population of objects that Webb has been uncovering across its now several years of deep field surveys, the objects nicknamed little red dots. These are small, extraordinarily distant, and strikingly red points of light that have shown up again and again in Webb's deepest images in far greater numbers than anyone expected. And their unexpected abundance has left astronomers genuinely puzzled about what they even are. Some little red dots appear to be little more than a compact galaxy. Others, on closer inspection, seem to be something closer to a swirling cloud of hydrogen and helium gas circling an enormous, actively feeding black hole with barely a galaxy to speak of surrounding it at all. One of the most striking examples of this second category came from an object called Abell 22744, QS01, nicknamed QS01, magnified and split into 3 separate images by the gravitational lensing effect of a massive foreground galaxy cluster known as Pandora's cluster, a natural cosmic magnifying glass that let Webb study it in far more detail than would normally be possible at that distance. Initial analysis suggested QS01's black hole weighed in at roughly 40 million times the mass of our Sun. But for a long time, astronomers weren't fully confident in that number, because every previous mass estimate for black holes this distant had relied on indirect methods, essentially educated extrapolations based on how black holes behave in the much closer, much better understood modern universe. As one of the researchers involved in the follow-up study explained, before this work, every mass measurement of a black hole in the early universe rested on assumptions borrowed from what astronomers already knew locally, without any way to confirm those assumptions actually held up across billions of years of cosmic history. When the team went back and found a way to measure QS01's black hole mass more directly, the number held. It really was that heavy. And more importantly, the surrounding structure suggested something that upended a fundamental assumption about how galaxies form in the first place. This black hole appeared to have formed before its host galaxy existed in any meaningful sense. Not alongside it, not after it, but first, sitting there as a kind of gravitational seed waiting for a galaxy to eventually grow up around it. That finding cuts directly against what's sometimes called the cosmic chicken and egg problem, a debate that's occupied astrophysicists for years. Did galaxies form first, gradually assembling enough massive stars that some collapsed into black holes, which then merged and grew into supermassive giants over time? Or did black holes, in at least some cases, come first, forming through some other far faster mechanism, with galaxies only condensing around them afterward? For decades, the conventional wisdom leaned toward galaxies first, stars burning out into stellar mass black holes gradually merging and feeding to build up mass over enormous stretches of time. But that slow, steady process simply doesn't have enough time to produce a sun-out massing by tens of millions black hole within the first 500 to 600 million years of a nearly 14 billion-year-old universe. It's not just a stretch. Under the traditional model, it may not be mathematically possible at all within that window, so researchers have been chasing an alternative explanation. and one that's gained real traction through published research in 2025 and into 2026 involves what scientists call direct collapse black holes. The idea, in plain terms, is this. Under very specific, rare conditions in the extremely early universe, massive clouds of pristine primordial gas that hadn't yet formed into stars, may have collapsed directly and catastrophically inward, skipping the star formation phase entirely and collapsing wholesale into an enormous black hole from the very start. Rather than the slow accumulation of a small stellar seed growing over billions of years, these direct collapse black holes are theorized to have been born already massive, containing tens of thousands to hundreds of thousands of times the mass of the Sun within just a few 100 million years after the Big Bang, giving them an enormous head start that would help explain how billion solar mass black holes could exist less than a billion years into the universe's history. If that theory holds up under further observation, it would mean some of the earliest black holes in the universe weren't born small and patient. They were born already gigantic, monstrous from their very first instant of existence, a genuinely strange and almost unsettling idea once you actually sit with it. Now, in the spirit of giving you the full, honest picture rather than just the most dramatic interpretation, it's important to walk through the pushback too, because that's exactly what real, functioning science looks like, and it would be dishonest to leave it out. Not every researcher is convinced these black holes are quite as overmassive or quite as rule-breaking as the most dramatic headlines suggest. A separate team of astronomers, publishing research in June of 2026, proposed a more conservative explanation for at least some of these so-called overmassive black holes. Their argument centers on a process called super-Eddington growth, an extremely rapid feeding phase where a black hole is consuming material so fast that the resulting radiation actually obscures it from certain kinds of detection, particularly X-ray observations that astronomers would normally expect to see from an actively feeding black hole of that size. Their modeling suggests that some of these black holes may not be as record-breakingly massive as initial estimates suggested, and that a plausible, less exotic feeding process, rather than a fundamentally different formation mechanism, could account for at least part of what's being observed. This doesn't erase the mystery entirely, and it doesn't apply to every single little red dot or overmassive black hole Webb has found, but it's a genuine, serious scientific counterargument published in a peer-reviewed journal, and it's exactly the kind of check and recheck process that keeps astrophysics honest rather than chasing every dramatic headline as settled fact. That tension, some researchers pointing to a genuinely broken model requiring exotic new formation mechanisms, others arguing the standard picture might survive with more careful, conservative reinterpretation of the data, is precisely where this field stands right now, unresolved, contested, and very much alive. And that unresolved tension is honestly the most exciting part of this entire story, because it means we are watching real scientific discovery happen in real time, not a finished textbook chapter being read back to us, but an open question being fought over in journals, in conferences, and FIs, org headlines, and astrophysical journal letters papers, by people who genuinely don't yet know how it ends. It's worth pausing here to really sit with the scale of what these instruments are capable of, because it puts everything else in this story into perspective. The most distant confirmed galaxies observed by Webb so far sit at a redshift of 14, corresponding to a time when the universe itself was only about 300 million years old, roughly 2% of its current age. Some astronomers are actively pushing observations even further, searching at redshift 15 and beyond, hunting for the very first galaxies that ever formed, the true starting line of cosmic structure. Every time Webb pushes that boundary a little further back, it isn't just adding another data point to a chart. It's testing, directly, whether our entire framework for how the universe assembled itself, star by star, black hole by black hole, galaxy by galaxy, actually holds up under the weight of real observation, or whether it needs to be substantially rebuilt. And this isn't just about black holes and galaxies existing early. It's about what their existence implies for the underlying physics of the earliest universe, the conditions of density, gravity, and matter distribution. In that first sliver of cosmic time that we're still working to fully understand, if direct collapse black holes really did form the way some researchers are proposing, sidestepping the star formation stage entirely and collapsing straight into massive black holes from clouds of primordial gas, that tells us something new and significant about how extreme, how violent, how different the physical conditions of the infant universe truly were compared to the comparatively calm, well-ordered cosmos we observe stretching out around us today. There's also a broader pattern worth acknowledging honestly, because it connects this specific mystery to a wider moment happening across astrophysics right now. Webb has, in a real sense, been quietly forcing a reckoning across multiple corners of cosmology simultaneously. The overmassive early galaxies, the overmassive early black holes, ongoing separate debates about the precise rate at which the universe is expanding, a long-running puzzle called the Hubble tension, where different measurement methods stubbornly keep producing different answers. None of these are proof that our fundamental understanding of the universe is collapsing, and it would be irresponsible and misleading to frame it that way. But taken together, they represent a genuine, serious, ongoing period of tension between what our best theoretical models predict and what our best instruments are actually observing. And moments like that in the history of science have historically been exactly when major breakthroughs eventually emerge. Not because the old models were worthless, but because they were incomplete in ways nobody could see clearly until a new instrument came along, powerful enough to expose the gaps. That's really what Webb represents in this story. Not a machine that handed scientists a shocking answer on a silver platter 4 minutes before you started watching this. A machine that keeps handing scientists a series of increasingly uncomfortable, increasingly fascinating questions, forcing them to go back again and again to models that have stood largely unchallenged for decades and ask, honestly, whether those models can survive contact with what's actually out there. Sometimes the answer, at least so far, is a qualified yes, with some conservative reinterpretation, as the Super Eddington growth researchers are arguing. Sometimes the answer looks more like a genuine no, requiring entirely new formation mechanisms like direct collapse black holes to make sense of what's been observed. And in a lot of cases, right now, in the middle of 2026, the honest answer is simply that we don't fully know yet. And more data, more observations, more careful follow-up studies using instruments like ALMA alongside Webb are still needed before anyone can say with confidence which explanation wins out. If there's a single thread tying all of this together, it's this. For most of human history, the night sky was something we could only look at, never truly look into. We saw points of light and told stories about them, the same way earlier civilizations told stories about the origin of everything, filling gaps in understanding with myth, because myth was the only tool available. Webb represents something categorically different. It's not a story about the universe. It's a direct, physical, time-delayed photograph of the universe's actual ancient past, arriving at our instruments after a journey of literally billions of years, carrying real information about real objects that genuinely existed at the dawn of cosmic time. When that information doesn't match our models, that's not a flaw in the storytelling. That's the universe itself, quietly, patiently correcting our arithmetic. So no, nothing was detected 4 minutes before you clicked on this video, and no single object has, in one dramatic instant, definitively rewritten every textbook in astrophysics. What's actually happening is slower, stranger, and in its own way more genuinely thrilling because it's not over, it's not settled. Right now, in observatories and university offices scattered across the globe, astronomers are still poring over Webb's data, still debating whether objects like Canucks LRD Z8.6 and QSO1 represent a fundamentally new category of black hole formation or a more conservative feeding process we simply hadn't accounted for yet. The mystery of the little red dots remains open. The question of whether black holes or galaxies came first in the earliest chapters of cosmic history remains genuinely, actively contested. And somewhere, right now, Webb's mirrors are still open, still gathering photons that have been traveling toward us since before the Earth itself existed, still hunting for the next object that doesn't quite fit, the next piece of light from the deep, ancient past that might finally tell us how everything we can see around us actually began.